Pad flight. Go flight. We have an extra item which actually should be on the checklist. We need to check, Christian Ravn's data logger needs to verify the trigger signal. So we'll just do that in a minute. Over.
Very well, I'll note it for revision of the next checklist.
Welcome to the streaming of one of our tests here today. We are today testing a series of long burns of our BPM5 engine. We are starting in a few minutes with the procedures, and you can look forward to see a number of burns, I think 3 or 4 long burns. The purpose of this test is to find a way of controlling the oxidizer fuel ratio during a burn, and during each burn we will have a series of tests inside the burn where we ramp up the oxidizer fuel ratio during the burn several times, and we will see how that performs.
Man kan sagtens huske at få det tjekket. Vi skal bare lige bekræftes på, at nogen har set det. Jeg synes, vi gør det nu.
Fuldskov. Fuldskov flight. Du må godt lige tjekke, at vandsystemet på gulvet virker skift. Afvælder.
Vi skal også lige have tjekket, det andet vandsystem med en Suborbitals. Så vi ved, at vi tjekker vandet på den her manuelle ventil, der er på siden.
Ja, vi får lige vand ud herinde. Så lige have vand igennem systemet.
Flight. Can you arm the system in preparation for the trigger detection? Over.
checklisten bliver ved med at savle.
Propellant down.
Godt. Thomas, kan du ikke lige, pille slangen af?
We are streaming on YouTube, and we have a chat at the side of the video, and we are trying to answer some of
do
the
you have
questions on
questions
the
standby?
chat during the test. And we just had a question from Space TV who asks how many countries were involved in development of the BPM5 rocket engine, and actually there's no countries involved in this. It's a private organization, and we are doing it in our spare time. So there's actually no countries as such. Only private persons. We are expecting, as I told earlier, 3 to 4 burns today, if we're lucky. And all of these burns will be tremendously long. I'll try to update you on the how it goes, and just hold on a second.
Flight pad.
Go, Pat.
We checked the lower firefighting suppression. It is operational. Can I borrow the net for checking the upper fire suppression system over?
Yes, can you do it without spraying the test stand with water over?
Yes, indeed we can. Bulskov, Jakob, over. Bulskov, kan du tænde den anden pumpe, som du havde, er den du tændte før skift?
Det kan jeg sagtens. Kom nu. Bør køre nu.
There was a question about the buzzing sound. We have actually microphone in the test container, and it's on. It's on all the time. So that may explain the buzzing sound you hear sometimes. During the Nexus 1 launch in last summer, we experienced
Yes, we can continue the checklist, and I can confirm that both firefighting suppression systems are operational. Over.
Thank you very much. Pyro flight.
okay, they're running the checklist. I'll just wait and sit back.
Pyro, we are at step 33. You are go for installing and connecting the pyro. Over. Pat?
Suggest moving on with step 34 while Pyro is working over.
Yes, we will commence. Booster, flight. Booster. We're at step 35. Are you go for loading fuel? Go for loading fuel. Alright, then we have a green board for loading fuel. We will now open the fuel vent. Fuel vent is open. Booster, you may commence fueling. Report when completed. Okay.
During the Nexus 1 launch, we had an issue concerning the oxygen fuel ratio. We saw a rocket majestically lifting itself very, very slowly over the Eastern Sea, and it never reached a speed more than 81 meters per second. So it barely were able to lift itself from the ground. Actually, the problem was that it wasn't fed with enough oxygen, so we ran very, very fuel rich, and the result was we didn't have enough power to go as high as we expected. It should have been somewhere between 6 and 10 kilometers at apogee, but it only reached a bit over 1500 meters. That's a mile. So before it went straight down to the sea again. And this problem with the OF ratio is very important to have a solution for. So we are trying to manipulate this ratio by changing the pressure on the fuel tank and the oxygen tank during the burns. We will start at 12 bars pressure in the chamber, and during the test we will slowly go up to 16 bars. During this we will have to manipulate the OF ratio by dynamic pressure system, where we change the pressure on the tanks. So in an experiment to see if we can make an exact control of the OF ratio. There's an interesting question on the chat from Robson Hahn. Why did you not use electric ignition, spark plug and so on? Well, actually, a system that really works is this pyrotechnic system. It's used on Soyuz, and it's used on a lot of other rockets, and it almost never fails. The electric ignition will, if we use an electric ignition, I'm myself working on one. We have to change the motor construction to use an electric ignition, and we are working on different kinds of methods for this. As it is now, the best and most safe method is a traditional pyrotechnic device, and that is what we see on the screen right now. Pyro is installing this gadget. We have very strict safety procedures concerning this, so right now there's only him and a spectator at the site. There's a question on the chat whether it's dangerous to be in the front of the nozzle installing a pyro. Actually, the system is not pressurized, so there nothing can happen. And if the pyro itself went off, it would only generate a few sparks. It's absolutely not dangerous in any way that we can think of. Well, the pyro might have burned hands, but that's all that will happen.
Booster. For at være sikker, I bruger nitrogengas lige noget, ikke også? Det er korrekt. Ellers skal vi glow det. Jeg troede ikke, I var færdige med det. Nej, vi har skiftet dunk. Det er modtaget slut herfra. Go pyro. Go pyro. Last flight. Booster. Ja, go booster. Jeg er færdig med at fuel. All right, then we will close vent fuel vent valve.
Well, Daniel K asked how long it will take to load fuel and oxidize. I can tell you that the fuel has already been loaded, so there's no problem there. The next thing is the LOX tank, and I believe we only have to pressurize that. But let's see.
Go pyro.
On the screen you can actually go down to the right corner, and there you can change the settings. If the little sprocket wheel, you can use that to change the quality, and you can go actually up to HD. And furthermore, you have the possibility to change camera. We have two feeds. It's the main feed, and then there is a mosaic feed where you can see, as it is now, 4 cameras from different angles, where you can change between these.
Go pyro. Thank you. Photo flight.
Photo, yeah.
We are at step 38. You are go for starting your slow speed cameras, over.
Roger that.
Logs right.
Log, sir.
We're at step 39. Can you confirm the nitrogen purge line pressure? It's still above 10 bar. Over.
Confirmed and confirmed.
Alright, was that step 40 you also confirmed? Over.
Confirmed.
Alright, crowd alpha, flight side.
Crowd alpha.
Is the test area safe? Over.
The test area is safe.
Alright, this is flight. All non-essential personnel should evacuate the test area.
Photo.
Well, we are almost ready for first firing. And
We are ready.
there was a question about how long
So your slow speed cameras
burns.
are rolling,
We
over?
expect to burn
All the
somewhere,
slow speeds are
some
rolling.
really long,
Thank you.
somewhere between 30 and 50 seconds. And we are using
Booster flight.
slightly larger tanks.
Please confirm step 44 that you will go for LOX loading, over.
Go for log loading.
We have the possibility of loading 48 kilograms
Flight
of
flight.
fuel and approximately 60
Step 45, are you go for
kilograms
LOX
of
loading, over?
LOX.
Alright, that completes step 46. We are go for LOX loading. We will open the LOX vent valve now. LOX vent is open. Alright, you are go for loading liquid oxygen. We are aiming at 50 liters, over.
Okay.
It seems I was a bit fast. We are not completely ready for the first burn because we have to load the LOX first. We are aiming at 50 kilograms, and with a, you can make the calculus yourself, with a OF ratio of 1.3. It's just a matter of calculating how long it will burn.
Yeah, LOX, this is flight. I'd like to
we have a
correct
question about the LOX
expected
remains the
LOX
limited thrust
to
factor. Actually, we that's a sponsor. We have been sponsored. We are the LOX is one of the few free things we have. We have a sponsor who delivers this for free, so that's not really a problem. But as earlier told, we would like to have a sponsor in the alcohol business. So maybe some Scottish brewery could send us a few hundred kilograms of bad whiskey. That would be really good. Well, we are loading the locks right now. We have a high pressurized system with a helium tank. I believe it's about 300 bar, and it will be pressurizing the tanks when we need it. It shouldn't be many minutes till we're ready. As you see, the test stand on the video, the test stand is actually one of the best things we have made for a long time. It makes it possible for us to test a lot of engines, a lot of motors in different ways, changing the setup very fast. You can see a lot of warning signs on it. That's because we have to be sure that everybody knows exactly which which tubes are used for what, and what we can expect when there's, example, a leak or something like that.
Let us aim for 55
There's a question
meters.
about the water percent. Question about the water percentage in the fuel. We are working with 75% ethanol. It's not ethanol. It's a mixture, ethanol and 10% of propyl. Oh, what is it called? Alcohol with 3 C atoms. No, and then we have 25% water. It makes the temperature, the combustion temperature, a bit lower, and because of the 25% of water in the fuel, we have a lot better cooling around the chamber. There's a question about the camera just below the engine. Will it survive? Yes, it will. We have tried this a lot of times, and the flame is very, what is it called? It's very slick. It's very distinct. There's not a lot of flames around outside the nozzle. There'll be a short burn during the purging later on. You will see a lot of flames, but it doesn't matter. It's just a very short time, and we have had lots of cameras completely bathed in burning alcohol. They survive. Isopropyl. Yes, that was a nice guy called Bailey who helped me.
55.
We're almost ready for the pressurization. There's a few liters left of logs we need, and then we are clear to pressurize and count down. So look forward to this. It'll be very exciting. I'm afraid this is gonna be the longest burn ever, but let's see how it performs.
That's it. Yes, we are happy.
Flight over.
Yeah, go.
Is that a confirmation of 0.51 over?
It is. So you may vent the log fill line. That is step 52 over.
Flight, this is pad. Logs line is vented out.
Thank you. Alright, the logs loading process is completed. Right, photo, right? Photo here. Please start your high-speed cameras. Right to that. Bo flight.
Oh, yeah?
Please stand by for arming the igniter system, over.
I am standing by.
Right, we're just waiting for photo to finish.
There's a question on the chat for fast update in Danish, so I will just change to Danish for a short moment. Update på dansk. Vi tager et stort burn her, eller faktisk 3-4 i løbet af dagen her. Vi kører en testserie, hvor vi faktisk kører ind i hver lange burn. Kører en serie af tests i samme burn, hvor vi ændrer på trykket og kører efterhånden. Så skal vi køre fra 12 bars kammertryk op til 16 bar kammertryk. Det er rigtig højt. Og se hvor godt det kan gå. Og vi er faktisk ved at være klar til første burn lige om et øjeblik. Der er installeret pyro, der er fyldt fuel på.
Vi er færdige.
Og der er fyldt logs på. Nu er vi lige ved at være klar til tryksætning. Så ja, det er bare at vente og se hvad der sker. Yeah, we are almost ready. This.
We have some function in power especially because the short circuit does save the pyro. We have some voltage on the system.
Could you repeat that?
whole system is malfunctioning right now, so we have to put a hold on it.
All right.
Well, we are almost ready for the burn. Pyro is ready. The fuel are loaded. The logs are loaded. We have to pressurize it and count down. And right now we are running a safety procedure concerning the pyro. It is well, there's a special plug among other things. There must be removed before it's even possible to ignite it, so we have extra security there. There was a question about the quality of the hoses, and among other things we're using in this setup. Actually, we're not. It's not any special aviation grade materials we use. We are experimenting with the different materials, and when we find a material that works in cryogenic temperatures and can shortly withstand a burn, we accept it. It doesn't have to be a special aviation grade or space grade, so on. Among other things, the whole motor itself is made of standard construction iron, not any special aviation grade material. It is actually common weldable steel. There's a good question about copper for probably for the motor. Actually, copper is really good material, not very expensive, and it leads heat very good. But the problem with copper, pure copper, is that when you heat it up at just 250 degrees or so, it gets very soft. So that's why standard steel actually has a lot of properties that are very beneficial. After the BPM5 engine, we are working on the larger engine, as we talk about. It's a BPM 100 that is a 100 kilonewton engine. Whether we will use one big engine or we will use several smaller ones hasn't been exactly decided yet, but as it is now, it looks like the best solution is one big engine. We will surely come back to that later on. There's a question. There's a question about stainless steel. Stainless steel is not very good at withstanding high temperatures. It can withstand high temperatures, but it wrinkles and it doesn't lead heat very good.
This is Mission Control out.
We have a bit of delay in the pyro system because we have the double check for the pyro. When we install the pyro, we check if there's connection to the pyro before we activate it. And it seems that the connection, it doesn't see the pyro installed. There can be a lot of small details that I don't know why it is so, but maybe it's just a loose connection or something. We are looking into it. That's a good question about how we get the money for this, because we are actually all volunteers. There is no one here that gets paid for anything we do. It's completely volunteer. We are using our spare time for this, and we pay a lot of our own money for this. And furthermore, we get something sponsored and something we can't get sponsored. We receive donations from a lot of people. That can be sometimes students, and sometimes businesses, and private persons, all kinds of things. People are paying to feel good about following us, and somebody sends us a few dollars, and some sends us thousands of dollars. It all depends on what people can afford. We have supporters from all over the world, from Japan and Brazil and United States and Canada and so on. We are being followed by a lot of people who send money to us. Actually, I believe we are. It is now possible to pay in bitcoins. So we are. There's a lot of possibilities to support us, and we would be very happy with if some of the followers would pay a few dollars to help us further.
Mission control out.
There's a question how to donate. Actually, you can go to our website, copsop.com, and there you can see a lot about our history, and you can donate in there.
Flight photo. Ja, go. Ja, færdig. Tak for det. Pyro, you are go for arming, over.
Copy that. Quiet, Pyro.
Go, Pyro.
The system is now on. Test stand for personnel.
Alright, that was step 56. You may evacuate the test stand and bring everybody with you. That is step 57.
Doing that. Flight Pyro.
Go.
We have evacuated the test stand.
Thank you. Pat, can you confirm test stand is clear?
This is Pat, test stand is clear.
Alright, everybody, this is flight. Pressurization is imminent. This is a DVR burn.
Well, the test stand is clear, and that usually is a good sign. It means we are all ready for the burn, and it should be there in a few seconds, I think.
Water, fire suppression, go.
Photo. Photo, go. Pyro.
Go.
Data. And data's go. Okay, we have green board step 67. We are arming the ignition circuit, step 69.
The go no go sequence has been performed, and
Alright,
we
we
are
will
now ready
commence
for the
pressurization.
burn. Yes, that's a pressurization first, and it will go very fast. We have full tanks, almost full tanks, and I will
Lux tank
please
is closed.
just listen to the countdown in a few seconds.
Alright, we are pressurizing the fuel tank. Fuel tank is at 18 bar. We'll now pressurize LOX tank. LOX tank 17 bar. We will commence 30-second auto sequence start in 3, 2, 1, go. Alright, 25 seconds. T-minus 20. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. depressurizing fuel tank.
Okay, that was the first burn.
All
We're
right.
sitting in a...
Booster, you may approach. We are pressureless. Okay.
Our studio is located in a camping wagon inside a building 250 meters from the engine. We could really hear that.
This is booster, all is looking good, and photo can come and shut off this camera.
All right, photo, you may approach and shut off your cameras. Photo, roger that.
Yeah, the system has been depressurized, so now people will run into the area, and it's completely safe right now. There's a comment on the camera. It was shaking wildly. Yes, everything around this test will be shaking violently. So we have earlier had problems with servers being too close to the test, so we don't have hard disk servers in the neighborhood of a test stand any longer, because they just stopped working. So I think we will maybe will have some better views later on when we come back after the test. We will maybe have better footage from cameras filming long way, very long distance away from the test stand. But right now you unfortunately must live with shaking cameras.
That is out here today, about 50 people coming in to have a look at the engine. It looks like we had a very nice and nominal burn. Pretty much everything worked as it should, except that one relay that malfunctioned in the beginning. We changed the relay to a different one, and yeah, everything worked, and it seemed we had a chamber pressure around 16 bars. More will follow when we are looking a little bit more on the numbers, but right now, everything is happy, happy, joy, joy. Mission control out.
That was a little briefing from Mission Control. They are very happy up in Mission Control, and the test stand had survived. You can see the one of the hoses is covered with ice. That's quite nominal, but maybe a little more this day, because we have actually here in Copenhagen on Refshaleøen, Refshale Island, and in Copenhagen we have a lot of fog. So maybe the fog has condensed on the hose. It's very beautiful, I think. It's the LOX is minus 183 degrees Celsius. So there's good reason for the ice to build up on the hose there. Right now you'll probably see a lot of people coming around the test stand. They are visitors here to see the test, and they have kids with them, and they are packed good in hot clothes, because we have 2 to 3 degrees Celsius outside here. It's quite cold, and all the people that are visiting us are allowed to come close to the test stand and see what we actually are doing, and it is completely safe because we have no pressure anywhere. Well, as you can see, it's possible for the guests to come and touch the engine and take photographs. We are quite open about these things. A lot of rocket companies around the world has to keep things very secret because it's business secrets and so on. For us, we are not trying to earn money on this. Therefore, we can use our efforts and our rocket engine, our launches, and all the things to education and enlightenment in the technical issues of rocketry. And we can do that freely, and we try to do it. Oh, there's a question. Will BPM 100, if it will be built exactly as one engine, going to have gimbal? Yes, it will have a gimbal. The system we are using right now is rudders stuck into the flame, which turns and by this turning changes the flame's direction, so we can control the trajectory of the rocket. But that would be a very massive system for a BPM 100 for BPM 100 engine. So we will use a gimbal. That's rather clear. Well, as you have seen, if you were with us earlier, we have had a tremendously successful test burn here. I believe it's the longest we have ever tried with this type of engine. And right now we have the visitors looking into the whole thing, and in a few moments we will send them out in a safe distance, and then we will commence with preparation for the next long burn. We don't have any data right now, but maybe we can have the flight director come around and tell us about what he has learned from the burn until now. But for the time being, we will be have a short pause from in the speak. And then we will return in maybe 10 minutes or so.
These are the parts for the BPM5 liquid rocket engine that we are currently producing at Copenhagen Suborbitals. If we're going to go over them piece by piece, the top piece here is what we call the LOX dome, and this is simply to inject liquid oxygen into the combustion chamber, or sorry, into the injector phase. So we feed liquid oxygen through a port. We have a pressure port on the other side to record the inflow pressure of liquid oxygen, and the liquid oxygen then exits from these holes at the bottom of the dome. They go into the top flange, as seen here, and in this flange will sit the monolithic injector that presently isn't completed, but the liquid oxygen exits these fairly large holes and goes into the top of this injector cup shape, and is then piped into the combustion chamber through a series of very small channels, 0.9 millimeter channels, through that injector plate. In between the LOX dome and the injector plate, we also have a strainer filter, and this is placed here simply to take out any foreign objects that might be in the LOX tanks or in the piping. And the issue here is, of course, that as the injector uses so tiny holes, 0.9 millimeter in diameters, it's fairly sensitive to plugging from smaller objects. And in essence, just plugging a single hole can be detrimental to an engine of this type, as you might end up with a complete skewing of the mixture ratios near the chamber wall, or any other position that might actually damage the engine or cause a burn through. So the filter parts are fairly important in this regard. The top flange here is a steel, a stainless steel object, and it consists of simply a ring of holes at the perimeter through which the fuel is entering the chamber. So if you remember the injector plate, it has liquid oxygen going through the holes along the longitudinal axis into the chamber, and the fuel enters from the side into the injector plate, and then it goes through a series of radial channels into the injector plate, and then is sort of diverged 90 degrees into the chamber as well. So the fuel flows. This is the inner chamber tube, so the fuel flows on the outside of this into this small recess here, and then goes through this 90-degree bend to exit these holes, and then into the injector plate, and then back down into the combustion chamber. This, of course, means that, as you can see, there are quite a number of twists and turns in the path of the fuel in the engine. And this means that you will see a considerable pressure drop going from the tank pressure to the combustion chamber pressure. This is, of course, something you would want to minimize, because it means you would have to use larger pressures in your tanks, and larger pressures means heavier tanks. So if you look at this part, you will notice that this has a slightly larger diameter than the other one. This is the outer skin of the rocket engine, or the chamber liner, or outer liner, so to speak. And this will in fact be cut into two along this axis, and then welded together on the outside of this chamber. To form the correct spacing between the two chambers, we use 2 millimeter copper wire that simply is soldered onto the inner chamber. And this then provides the correct spacing. I have another engine over here. Simply we put these in to inundate the concept of keeping those spaced adequately. And the concept is, of course, we want to make sure that we have a fixed and well-established spacing between the two walls, so to give the best possible constriction of the flow volume on the outside of the inner chamber. To get the fuel into this volume in between the two engine cylinders, we will be using a manifold which will be welded to the outer rim of the outer liner of the engine. So this is one of these manifolds. It will be cut diagonally and then welded together on the outside here. Fuel will enter the manifold through a pipe that goes along the side of the engine, and the fuel will then swirl around in this volume and then be directed up in the spacing between the two chambers. And the flow will be directed by these copper spacers as well. These spacers are going to go along the longitudinal axis, and then it's going to do a small twist at the end, sort of just to direct the flow in the axial direction. If one wants to add another remark to these spacers, the concept is that you can use these spacers to control the flow velocity in the cooling channel. And there are many ways to do this. One way could be, as we've done here, simply to make it along the longitudinal axis, which will give you a fairly low flow velocity, but in a sense that the flow will be non-turbulent over the largest part of the volume. Another option would be if you need more cooling capacity, or you want to harness more of the cooling capacity of your fuel, you could do a spiral that goes around the inner chamber, and that will increase the flow velocity, but also the distance traveled by the flow as it goes from the manifold and into the injector and into the engine. And this means that it'll readily absorb more energy from the combustion chamber itself. This can have an advantage in the sense that you harness more of the heat capacity of your fuel, but it could also have the disadvantage that you get closer to the boiling point of the fuel at that given pressure, the operating pressure. So this is a trade-off you can do. Essentially, it's a parameter we can adjust later on if we feel that we are operating marginally in terms of thermal conditions. We can we can change the format of these spacers to better implement cooling in any part of this volume. You could imagine a scenario where around the throat of the engine you will see the largest heat flux from the combustion going through the inner liner. So you could envision a scenario where you want to increase the cooling capacity at that particular point, and that can be done by changing the geometry of these spacers. So this is one of the features of this engine. Essentially, this allows us to better tailor the thermal response of the unit. So here we have one of the main valves for the BPM5 engine. We have two main valves, one for liquid oxygen and one for the alcohol fuel mixture. And as you may remember from previous tests in Copenhagen Observatorials, all of the engines have been operating with a pre-stage, main stage architecture. And the idea has been that you open a pre-stage valve to get a slight flow into the engine, and then you ignite that flow to ensure complete ignition prior to actually opening the main valves and then starting the engine at full thrust. And that concept can be used to sort of ensure that you have a stable ignition source present in the chamber prior to actually firing up the engine at full throttle. And in essence, that's done to make sure you minimize the risk of a hard start. Presently, that configuration required two valves for fuel and two valves for oxygen, or for liquid oxygen. So that's a weight and shall we say complexity challenge. For the BPM5 engine, we've chosen a slightly different strategy in that regard. We have chosen to do a single valve solution, but a valve, rather than the previous setups which have used pressurized air to simply move the valve from closed to fully open, we have now a electrically actuated, electric motor actuated valve instead that allows us to move the opening degree, or the degree of opening in the valve, with quite a bit higher precision. So in essence, we are now using a valve with a cross-section like this. So it's not a straight hole anymore. And this means that when you rotate that valve inside this ball inside the valve, you'll be able to open a very slight flow at the beginning, and then you can open it fully to get a full flow through the valve. And this means that we can actually do the pre-stage, main stage architecture with the single valve, and we have full control over the mixture ratios between the liquid oxygen and the fuel as the burn goes on. And this means we have a whole new set of options in terms of driving the motor at the correct operating point all the way through the burn. We don't have to accept that the point of optimality will only be at one point. We can sort of trim this as we go along to sort of correct for the autogenous pressurization of liquid oxygen once the tank is depleting. So that's a whole new option for Copenhagen Suborbitals.
Så flød jeg den af.
Det man kan frygte, hvis det er langsomt flowet zone.
Some stuff together before.
The next one launch is the first time we have an opportunity to see how our own CS2ino computer variant of the Arduino system is behaving in a launching rocket. We have developed our own version mainly because we need a mechanically more stable version, more rugged version than the original Arduino. And I for one am very anxious to see if our efforts will pay off and it will behave as we expect. We have 4 Arduino computers in the rocket. We have one in the engine controller in the base end of the rocket. We have one in the guidance and navigation system, and we have 2 CS2inos in the radio system to have redundancy in the telemetry system. For the engine controller, we have made an interface board that caters for the specific interfaces we need in the engine controller for the various pressure sensors, temperature sensors, and to drive the actuators and solenoids throughout the rocket and the engine compartment. To charge the batteries inside the rocket, we have opted for using a couple of commercial off-the-shelf ready-made chargers that we have put in our flight case, and so we can both charge the batteries in the workshop and in the harbor, and also at sea at the launch platform.
My name is Flemming Nybo. I work with guidance and navigation. And guidance is the effort of making the rocket fly straight rather than simply flying like fireworks. And navigation is needed for guidance because navigation is the technology to determine where the rocket is in space and how it is oriented. Now, the rocket actually does have GPS, but we don't use it for guidance and navigation. And that is for two reasons. One is that due to the acceleration of the rocket right after launch, the GPS receivers are likely to lose their fix. Another reason is that GPS tells you where you are at, but it does not tell you how you are oriented. And that latter part is important to steering a rocket. Let me give you an example. If the rocket is here, and from its position it knows that it should move over here, then that requires some steering action. But then if you imagine that the rocket might as well be rotated like 90 or 180 degrees, then it actually requires the opposite steering action from the driver's perspective to get over there. Now, the inertial navigation system we use instead of GPS for steering is based on gyros and accelerometers placed in the guidance and navigation computer in here. The gyros and accelerometers sense the movement and rotation of the rocket, and based on these sensors it incrementally calculates where it is at and how it is oriented in space. The actual steering determined by the guidance system is done by the jet vanes down here at the business end. There are various ways of steering rockets. Big rockets are usually steered by tilting the whole engine, but there's not a lot of space for such a system in here, though we are working on it. You can also employ aerodynamic steering like airplane steering. This is not used a lot in rocketry because it only works in the dense air close to Earth. Also, the aerodynamics of steering in that way are very difficult to predict, and such a system is very difficult to test on the ground because you can only actually see if it works when the rocket is flying. A more testable system we have chosen for Nexø 1 and its predecessor Sapphire is the use of jet vanes. These work like rudders behind the propeller on a ship. They sit directly in the extremely hot exhaust and turn by electrical servo motors to simply deflect the jet exhaust slightly to one side or another to steer the rocket. The challenge about jet vanes is to make anything that will not simply burn away in the exhaust. Sapphire flew with copper jet vanes, but because this BPM5 bipropellant engine has a longer burn time, copper did not work when we tested it, and instead it more traditionally uses graphite jet vanes, which can actually take the heat, though they get worn a bit during the burn, and after the burn they are hot enough to glow white. So this is the short story of the guidance and navigation system I'm working with on Nexø 1. Thanks for watching.
Well, this is the Nexø 1 rocket. The bottom, where we have the engine compartment, where all the flames come out, and we have the fins here. Up here, we have the section with the valves that controls the fluids, the fuel and LOX. And up here we have the LOX tank, and the LOX tank is 183 degrees below zero, so the paint is peeling off here, as you see. And here we have the intertank section with the Christmas tree. We'll look at that later. Up here we have the fuel tank with alcohol. And here again we have the upper intertank section with the Christmas tree here.
And here we have the electronics department, the Avionics section with the controller electronic. And here again the parachute compartment. And in the top of this we mount the nose cone.
My name is Morten. I am the head logistics guy at Copenhagen Suborbitals. My job is to make sure that everything we need actually gets to Bornholm in the right time for launch. It's a multi-tier operation. We have some deliveries coming directly to Bornholm from, for example, the locks for the rocket, and some of it we bring ourselves on our ships. But mostly we actually take the biggest part by truck. It's easier. It's more reliable, and it's just easier than packing it on the ships. If you pack it on the ships, you need to make sure that it's weatherproof, where you can just rent a truck, put it in the back, and everything is good to go. When we get to Bornholm, we borrow some facilities where we can store it, especially if we have a delay because of weather or other things. And we usually have containers and stuff on the quayside to make sure that we can actually store things while we're working, because the Danish weather is well known for being very unstable, so we don't want delicate electronics being destroyed by rain just because there's a shower coming in. So that is basically my job, is to coordinate all these things and make sure that everyone has what they need in the right moment. And it is a lot of administrative work and 10 minutes of usually very hard work to get everything over there. At the same time, I make sure that we get the rocket on to Sputnik. It takes a little bit of lifting equipment. Some of it we actually made ourselves. It's kind of specialized. It fits the rocket and the rail it's being transported on. We lift it down to Sputnik, and from there we can use a hoist to get it up onto the rail and get it secured. So getting all these things to come together, making sure we have the right equipment is also my job. Most of it is of course coordination, and then the rest of the guys help with the actual doing of the job. So that is actually my main responsibility during a launch, and my secondary responsibility is a bit of photography, but that is usually done from one of the rib boats at sea.
Confirmed and confirmed again.
All right, that includes step 40. Crowd Alpha, flight.
Miling, Carsten.
Crowd Alpha, flight.
Crowd Alpha goes.
Can you verify the range is clear? Over.
I'm currently working on lighting in the container, so I'm not sure. Stand by.
Sydporten er klar. Miling, Carsten.
It's clear.
Well, the speaker is back again. I had to show around in the workshop, and we are preparing out there on the test stand for the burn number 2. We had a tremendous burn the first time here earlier today, and they are preparing. I can see the pyro is already installed. They are trying to fix something about the cameras, but I believe we had the best burn ever here. So I'll be back in a moment with news.
Fly 5 photo.
Go photo.
Alle slowkameraer tændt.
Tak for det.
We have heard there's something like static or something like that on the feed, a little sound. We're looking into that, so we'll return with news about how, if we find the error. There's a question about if we use a solid motor to start the engine. Actually, we use like a New Year's fountain, spraying out magnesium flares inside the engine. It's quite small, but it has the power to ignite this engine.
Flight, vi er færdige med lys.
Tak for det. Alright, Pat, that means we're ready for logs loading. Can you verify the test area is void of non-essential personnel?
Well, if you have ever witnessed
Flight is
someone
over.
test earlier, you will know that there can be very, very long time between each burn.
Can you clear the test stand of unnecessary personnel for the logs loading? Over.
This has been completed.
But
Alright.
this time, using DPR,
The log
dynamic
vent valve is
pressure
open.
regulation.
So, Booster, are you go for logs loading? Yeah.
Because of this DPR system,
Logs, are you go for logs loading?
we can have a very short cycling time.
55 kilos of logs. So this is step 49. Over.
5 kilos. We will do this last time. Have a hold at 45.
The question whether the locks, very cool locks, can blow out the fountain during ignition. But we are actually, ignition is several steps. We are ramping up the power during the start of the ignition. We have, among other things, we have a pre-stage and a main stage. We start with pre-stage, and when we have confirmed that we have ignition, then we ramp it up to full throttle. Just a quick update for the new followers. We are today testing 3 or 4 times long burns, very long burns with full tanks almost, and we will during each of these burns we will ramp up the power of the ramp up the pressure on either the LOX or the fuel tank, so we can see how good we can manipulate the flow rate of the fuel and the oxygen. We have actually flow measurement on board this test stand, so we know precisely how our changing in pressure in each of the tanks will affect the actual flow to the motor. And this is one of the things we are trying to make with this. It's to see how good we can control this dynamic pressure regulation system. As you see up on the test stand, there's a big 02 mark that tells us that this is test number 2 today. And as I told earlier, we should be able to make 3 tests. If we are lucky, we can make 4.
Flight, Oxford.
So let's see how it goes.
Go LOX. Jeg holder den lige her i 2 minutter, ser hvordan den opfører sig, og så fortsætter jeg.
Ja, tak.
Well, there was a question on the chat, how do you confirm ignition with temperature or what? No, actually we know by experience that when we have a solid pressure in the chamber over something, I don't remember exactly how much, when we have this pressure, we know that the pre-stage ignition is perfect, and then we can ramp up the power.
Flight, LOX her.
Go LOX.
You happy?
Det ser mægtigt fint ud, Rune. Tak for det.
Så tager jeg nogle folk med ned til stenlaget.
Ja, tak.
Jeg tror ikke sten for meget.
Runde 59 kvadrat bag.
LOX flight.
LOX.
Can you confirm step 52 that the LOX fill line is vented over?
Confirm, yes.
All right. right, all stations. That means we're about to commence the pressurization. Photo, flight. Photo here. You are go for starting high-speed cameras. Okay. Pyro, you are standby for arming.
I am standby.
Well, as you can hear, the fuel is loaded, the LOX is loaded. They are asked to start the high-speed cameras, and they cannot run for very long time, so they are always started just before the burn. And we are ready for pressurization, and we are ready for connecting the pyro. So we'll have a burn in quite a few seconds from now. I can see they're starting the cameras right now. So we look forward to this burn number 2 today.
Flight, photo here. Go photo. We are go. Photo. Pyro, you are go for arming, over.
Okay.
Oh, I love when they say pyro is go for arming, because then we know what will happen in a very short time. And as I can see it, we have all the cameras running right now, so it'll be fun to see. But unfortunately, you will see a very shaky picture.
System is on, and the area is clear.
Thank you. Pat, can you confirm the area is clear? Over.
Affirmative, flight, pad is clear.
Alright, that means we're at step 58. Pressurization is imminent. This is a DVR burn.
Oh, it's very interesting. I see on the chat that Morten Bulsko up at the test stand tells that with thrust was 600 kilogram, or that is 6 kilonewton. That means we have been approximately 20% above what the engine actually is built for. That's interesting.
Alright, standby for go, no go. Ground Alpha, go, no go. Ground Alpha, go. Booster. Booster, go. Water.
Water 1, go.
Water 5 suppression, go.
Photo. Photo, go. Pyro. Pyro, go. Data.
Data go.
Alright, we have a green board. We will commence. Alright, we will pressurize the fuel tank. Fuel tank is pressurized. We will pressurize left tank. Auto sequence start in 3, 2, 1, go. T-minus 30 seconds.
Well, 25 seconds to burn. Are you ready? Look at your screen, see the
20
burn.
seconds.
It's 20 seconds, that's good.
15.
Everything is running, it's perfect.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, ignition.
Now that was a nice burn.
Feed 2.
And now we have the... yeah, it's purged now. They have emptied out the last part of the fuel and the logs, and now they are venting taking the pressure off the tanks, and as soon as they are taking off the pressure, the test stand is safe for approach.
Alright, booster, we are pressureless. You may approach.
I am inspecting the test stand. Okay, the test stand is safe. Photo can approach.
Having been a part of this project for a lot of years, actually since 2010, it's very interesting to see how much the procedures has been changed, how how it's we are more secure. We are have a shorter rotation period from test to test, and all the systems with high-speed cameras, the safety procedures, and so on. It's going better and better, and we have never had anyone who were injured during these tests. Never, actually. So that's a success in itself.
Foto, hvor langt er I? Skift. 2 minutter. Fly photo. Go photo.
photo is finished.
Tak for det. Okay, nu hvor foto er færdig, så er testeren åben.
There's a question on the chat about how if we can use the shock diamonds to see anything about the thrust. Actually, no, we can't do that. The only thing we know about it is that we are working at exhaust speeds above the sound of the speed of the sound. But there's then another question. Why not try to roast something in front of the flame? That could be funny. Well, we have tried. A piece of copper. It evaporated. It was a very beautiful green flame. There was another question about the thrust data. We haven't got much right now, but we can say so much that it seems we are about around 6 kilonewtons. That is 20% above the design parameters for the engine. Yeah. Yeah, well, people are running around patting the rocket. It's a fun thing for especially young adults and kids to experience. We will play a few video clips, and so we can have a little pause here. We will be back in about 10 minutes. 10 minutes.
This is the Nexo Run rocket at its current state of development, and it is the first liquid-fueled biprop rocket of Copenhagen Suborbitals, and only the second one ever attempted in Denmark. It should be considered shall we say, the light version of the Nexø class series of rockets that we're going to do here at Copenhagen Suborbitals. It's going to be using the blowdown operating mode, meaning that we're going to top up the tank pressures with helium, and then allow the tanks to deplete with the helium expanding directly in the tank. So the DPR system will not be available on Nexø 1, it will only be on Nexø 2 and forward. And this means, of course, that Nexø 1 won't get to the same level of altitudes as Nexø 2 will, but in essence the altitude is insignificant in terms of Nexø 1, as this is more a, shall we say, a technical test of the different systems that one has to master to do biprop rocket systems. So we will be looking much more for the performance of the individual subcomponents in the rocket and the overall design as such to weed out any, shall we say, misdemeanors or non-conformities in the design and optimize that towards Nexø 2. Also, one should always keep in mind that Nexø 1 and Nexø 2 are part of the roadmap towards the Copenhagen Suborbitals Speaker rocket. And the Speaker rocket will be the full-scale manned vehicle. In that sense, Nexø 1 and 2 aim to demonstrate and familiarize all the people here at Copenhagen Suborbitals with the technologies required to develop and fly a Speaker class rocket, which is a much larger vehicle than this, of course. But the advantage of this step, or intermediate step, is that all the techniques applied, they double to the Speaker class rockets. So what we develop and test on Nexø is the stepping stone required to do Speaker in the coming years.
Now, compared to its predecessor Sapphire, Nexø 1 is about the same length. It is 30 centimeter diameter, where Sapphire was 22. It is slightly heavier. It is not a much bigger rocket. We also don't expect it to fly faster or higher. So the change is all under the hood. Importantly, Nexø 1 flies our first bi-liquid engine. And we're switching to bi-liquid, though this is a major technology step, because bi-liquid has shown to be more scalable. So if we can make bi-liquid work and fly in this size, we have a design that can be scaled to a bigger rocket, whereas the hybrid motors are notoriously difficult to scale to bigger size.
My name is Thomas, and I am supposedly the project lead on the Nexø rocket. Now, fortunately, the crew working on the Nexø rocket they are so self-propelled that my job has been very easy. So my major contributions has more or less been calculations and the initial overall design, and then purchasing stuff for the Nexø rocket. I'm not myself a metal worker, so I've not been working on it myself, and fortunately the crew is very dedicated and working very hard on it.
Hello, my name is Jacob Larsen. I've been doing particularly two things with this Nexø rocket and the launch. The first of all is that I've been putting together several of the BPM5 engines we're using to propel the Nexø rockets, trying to learn how to best build them and how to improve the building as I went from one prototype to another. The second thing is that I'm a co-designer on the Nexø rocket, the mechanical airframe from the Avionics section and all the way down to the exhaust nozzle. What I'm particularly fond of already is this entirely new design procedure we've been using for the Nexø rockets, which is basically a modular, compartmentalized set of sections which you can bolt together and pull apart as you wish.
I'm Jonas Bjarnø, and I'm the technical advisor on the Nexø 1 project. And I've had the pleasure of doing the initial dimensioning and trajectory and performance calculations for the Nexø 1.
My name is Flemming Nybo. I work with guidance, navigation and control, which are the fancy terms for trying to make the rocket fly straight up. So, as you may know, we have had a jet vane that has survived a static test successfully several times. So we now know that Nexø 1 can be steered by jet vanes like its predecessor Sapphire. So as such, the navigation and control system architecture will be identical to Sapphire, and the core of the control system can actually be reused. There are also some changes. Besides the new jet vanes, the control system must be adapted to the physical parameters of a different rocket. That is, its mass, its inertial moments, and importantly how these numbers progress as it uses its fuel during the burn. Also, the system must be tuned for the specific aerodynamics of the rocket, and the aerodynamics of Nexø 1 have been modeled by Jonas Bjarnø, and the parameters from this work will be added into the control system. Also, we are flying with an analog devices eye sensor IMU. Sapphire also did that and flew with what I believe was the best MEMS IMU available for the purpose at the time. But since the product line has progressed since then, we now have the luxury of a slightly better performing eye sensor IMU. So we expect to get a little tighter navigation performance without any extra effort on our side.
My name is Jesper, and I made this Avionics section for the rocket, Nexø rocket. This is the part of the rocket where all the electronics and control equipment are placed. The GPS, the radio, and all communication for the rocket.
Hello, my name is Christian, and I'm the chairman of Copenhagen Suborbitals. For the Nexø project, I have mostly been a coordinator. I've been leading our weekly meetings, and my main contribution is to make everybody work together, figure out who is in need of extra help or extra resources, and have a look at the economy, making sure that the money will be well spent and that we will be spending the last kroner at the last day of the project.
Hiya, my name is Lily, and I mainly work on the turning lathe as far as the production is concerned. And for the Nexø 1 rocket, I've been working on the production of the dome and the alloy for rolls, which is what you weld on the tanks in order to be able to fit fit both the stainless steel and the aluminum together. And right now I'm working on the flange for the Nexø 2 rocket. So that's what I'm doing at the minute.
My name is Martin, and I have been designing a small contraption that links the electrical motor that controls the valve with the valves, the main valves for either LOX or fuel.
My name is Bo Brandstrup. I am responsible for the wiring and cable harness in the Nexø rockets. The cable harness is going from the Avionics bay at the top of the tanks, traveling in our cable channel all the way down to the engine compartment of the rocket, where it connects the avionics to the engine controller and the rudder servos. I'm also responsible for the cable harness inside the avionics bay, which connects the different modules of the rocket, batteries and the power supply and our guidance computer and our radio. On top of that, I also have assembled the CS Arduino boards and defined all the cabling inside the boxes for the modules.
Hello, my name is Stefan Eisenknappel. I am an intern here at Copenhagen Suborbitals, and I help the guys wherever they need me. And actually right now I am working on the baffles, bending the baffles for the rocket. It's like the shell, and looking if all the holes are lined up, and helping the guys with assembling. Also I am doing welding, so I was turning some fittings on the lathe, which goes to the LOX tank, and I'm also welding custom-made fittings, so I just weld them together. And well, that's what I'm doing, and I'm happy to be here.
My name is Rune Hensel. I have been doing the design of the nose cone, which is actually what we can see right here, in the process of being made. And then I have been doing all the LOX certification and cleaning of LOX parts that are in contact with LOX.
Hi, my name is Morten. I'm a member of the board in Copenhagen Suborbitals. And on the Nexø project, I have been doing what I usually do in Copenhagen Suborbitals. That means I have been running the logistics and the purchasing department, making sure that we get all we need at the right moment. I have been ordering the tanks for the rocket from a subcontractor and making sure that they actually delivered what we were supposed to get.
I'm Peter Mortensen. I am building a video transmitter for Copenhagen Suborbital that's going to fly on the Nexø rocket. The project was started by Alex, and I'm finishing the transmitter part, so we can try to transmit DVB-T down from the rocket down to the platform.
My name is Peter Meinke. I have made the most of the welding in the Nexø rocket, the pipelines. In the test stand I have developed the mount for the tanks, the LOX tank, and the most of the welding of the setup for the test jet drain. Also the jet drains mount for the Nexø rocket. That is the design of the rocket and the design of the test stand also been involved with.
Hi, my name is Flemming Rasmussen. I am a software engineer of profession. So that's the reason here in Copenhagen Suborbitals I mainly do mechanical design and manufacturing. I have the lucky position that I work in a company where I have access to 3-axis CNC milling, and thus a lot of tasks concerning that is coming my way. As an example, for the Nexø, I have manufactured and partly also developed a lot of the parts concerning the thrust vector system. Here we have the graphite jet vanes. Here we have the vane bearings, which I've all milled out, and together they form this beautiful piece of equipment that hopefully will point the Nexø rocket towards the skies. Unfortunately, on this project, I have not had too much time because my other job takes up a lot. So basically that's what I've been doing. But hopefully, I'll be back for this weekend with more inputs.
My name is Peter Scott. I'm involved with a number of different parts of the rocket. First, I've written the software for the engine controller that we use to control the engine and all the sensors and servos around it. Secondly, I've designed the telemetry radio system, which we use for getting telemetry from the rocket and down to Earth, and then also getting commands from Earth up to the rocket while it's flying. Third, I'm involved in the data transmission system for our video live stream system, that is getting the video data from the ships and all the way back to shore and onto our mixing system. And last, I'm involved in doing maintenance on Vostok, our command ship.
Well, welcome to the OB1 here at Copenhagen Suborbitals. This is where we are actually mixing the live stream. My name is Peter Marsk Møller, and I have been helping creating this system we have here. We have a couple of screens. We have a mosaic screen that we usually also send out into the live stream, and we have a premix and a postmix. The premix and the mosaic is taking place, being mixed in the Baltic Sea, and we control it here from Copenhagen. The postmix, where we add text and commentators, audio, we mix here in Copenhagen, and then we send it to YouTube Live. We have created a little system where we can control the mixers in the Baltic Sea, in the middle of the Baltic Sea, and we control both the audio and video. And that's about it. Usually we are a couple of people sitting here. We have one or two commentators, and then we have one or two taking care of all the technical streams. That's about it. I hope you enjoy our streams.
My name is Niels Foldager, and regarding the Nexø rocket, I have been involved in the engine group that designed the engine. I have dealt with the evaluation of the injector design. And regarding construction, I have dealt mostly with the airframe, where I have made a lot of milling and drilling, making threads, and being on this lathe here.
The Nexø design is the first rocket design of the history of Copenhagen Suborbitals that has been drawn in detail before building commenced. Thomas Madsen did the drawing and detailed mechanical and metal design work using the SolidWorks software. Thomas Madsen was also a part of the team that designed the BPM5 rocket engine and its one-piece CNC molded injector. After finishing the design work, Thomas Madsen has taken part in the manufacturing, assembling and final adjustment of the Nexø 1 rocket.
Nexø 1 kan sagtens stå her.
Jørgen Skødt has welded part of the Nexø 1 piping system, and furthermore he is part of the visual design team and in charge of production of labels and stickers for Nexø 1. Christian Ravn did part of the Nexø 1 rocket design, especially calculations. He also performed reviews on the other parts of the design. Christian Round designed and manufactured the burst disc system that serves as a secondary safety mechanism guarding against tank rupture due to unintended overpressure.
When you look at Nexø 1, you see a lot of threads and a lot of screws, but not so much welding. And the purpose of this is that the engine, the rocket is easier to assemble. Things can be bolted on and taken back off and fitted back on again during the process. And this is also more serviceable should something happen to the rocket that needs to be repaired. We have also had a different design process this time. Everything has been drawn in CAD beforehand, so we have known upfront how we would fit all connectors and pipes and wires so that nothing got in each other's way. And as such, this has been a good structured process, and also a process where it was easier to involve many people in a team effort because everything was planned ahead.
The other thing I'm looking very much forward to is seeing this seemingly very small engine propel this very large Nexø rocket high up in the sky. It looks, the engine looks small in the airframe when you're looking at it, but it's still good for more than half a ton of thrust. So it will definitely get off the rail. I'm just waiting to see how high.
The end of the roadmap for Copenhagen Suborbitals will be the Speaker rocket. And the Speaker rocket is our manned launch vehicle designed to carry a passenger vehicle of approximately 300 kilograms to an altitude of 100 kilometers or slightly above, so as to reach the Kármán line and bring back the passenger alive. It's a substantial rocket from an amateur perspective, and the technologies required to do that are those that we aim to demonstrate with the Nexø rocket series. And this is actually why we do the Nexø rockets as a stepping stone towards realizing Speaker. We need to demonstrate the ability to run biprop systems, all the control, the DPR system, the pressurization systems, the avionics involved, the recovery systems, and all those subsystems need to be realized from scratch because it's not technologies that were previously available in Copenhagen Suborbitals. And the Nexø rocket series will allow us to do that. The Nexø 1 rocket will be the first step down that path and will allow us to evaluate a biprop rocket system and in particular the startup sequences of the engine at sea, the operations associated with tanking and detanking and working with biprop systems in the rough environment that a sea launch does involve. And it'll allow us to work for the first time also with composite structures and more lightweight designs than we have previously worked with in Copenhagen Suborbitals. So the Nexø series should be considered a vital stepping stone towards the future of Copenhagen Suborbitals, the Speaker rocket series.
Logs, flight. Logs, sir. Should we stop the pressurization here, over? Let's go for 210. Alright. Flight to mask. Go mask. You have number 2 on the test stand. Alright, thank you. We will set it for 3. Thanks.
Well, after a short pause from the studio, we are back here. In the meantime, up at the test stand, 250 meters here from here, they have just fueled and they have filled the locks up, and they are preparing for the third burn. And I think I think they are just now changing the sign on the test stand so we can follow that. We know that it's test number 3. That's rather interesting when we are looking at the videos later on, that we know which burn we are looking at. So we are actually preparing for the third burn, and in the meantime I can tell you there had been some discussions about the weather in Denmark. Well, Denmark is a somewhat cold country, not as cold as on other latitudes around the world, but it's changing all the time, and just today it's foggy outside, and it's very cold, and but still above freezing point, and 3 or 4 days we are running down at -7 or 8 degrees, and then maybe 14 days after we are around 10 or 15 degrees, and so this is how the weather in Denmark is. So we are always prepared with extra warm clothing, and just this day we are happy that it's not blowing. The wind is not. There's no wind, and that's good. But it's very foggy. So you can actually see it on one of the pictures. Sometimes you will be able to, if you go to the mosaic feed down at the right corner of the video, you can change to mosaic feed, and you'll see that the feed number 1 is rather foggy. That's because of the weather. So that's how it is here. while we're waiting for the burn, I can tell you that it's always possible to go back. Possible to go back in the feed and see the earlier burns. They've got to go for turning on the low speed cameras. That means maybe 2 or 3 minutes left for the next burn. The last thing they do just before
Flight locks up. Go locks. Tak for det. Alright locks, that means we're at step 3. Confirm, I'll confirm. Alright, Crowd Alpha flight. Crowd Alpha 4 step 41. Crowd Alpha. This is flight. This is step 42. All non-essential personnel, please leave the test area. Booster, are you ready for LOX loading? Ready. LOX, are you ready for LOX loading? Ready. Alright, vent valve is open. You are go for LOX loading. Over. 55 as usual. 55 meters as usual. Same procedure as last time then. Fly photo. Go photo. Photo is done. With a slow. Tak for det.
We have a visit from New York, from actually one of the founders of the company Livestream.com. He's the person you see sometimes wearing a red jacket. He has some equipment. I think he's recording some video up to the left of the test stand. right now you see a feed with the engine, and you can see it's very cold down at the injector end, where a lot of ice has collected on the surface. It's because the LOX, the liquid oxygen, is actually 183 degrees below zero. So all the moisture in the air is frozen on the outside of this part of the engine. So you can see the temperature difference between the actual tube of the outer tube of the motor. It's that is 50 to 80 degrees during a burn, and just after, and and then we have the injector and LOX dome far below 0 degrees Celsius.
Flight LOX.
Go LOX.
Er du klar?
Yes. That was step 51. You are go for step 52. Vent LOX fill line. Over.
Done.
We have fuel loaded and the LOX is loaded, and the fuel line for the LOX tank is being ventilated, and then after that we will see a pressurization, and then we have a burn in very short time.
Alright, LOX loading is completed. Photo, this is right. Photo here. Please start high-speed cameras. And Pyro, you are on standby for arming the system. Copy, bud. Alright, this is flight. We are about 3 minutes from firing.
You can see a lot of people running around at the test stand. They are starting up the high-speed cameras right now, and as I told you earlier, this means that we are very short from a firing. We will not pressurize before we have these people away from the test stand. That's a security procedure. And the last man on the test stand is the guy who connects or close to the test stand is the guy who connects the pyro to the electrical circuit.
Flight photo. Go photo. Vi er færdig. Thank you. Pyro, you are go for arming the circuit. Over. Flight, Pyro. Go Pyro. Go Pyro. The Pyro is armed and the area is almost clear. Just turn off the lights and I'll be up. Okay, the area is cleared. Alright, this is Pat. We are about to pressurize. Ready for go no go? Crowd Alpha, go no go? Crowd Alpha, go. Booster.
We are running through the go no go session. That's
water.
Very classic.
Water is go on test stand.
Water suppression, go. Photo. Photo, go. Pyro. Pyro, go. Data. Data, go. Alright, we are ready. Alright, we will pressurize the fuel tank.
After pressurizing the oxygen tank, first the fuel tank and then the LOX tank, we will start a automatic system for the last procedure. That is, and when they start this, we will have just 30 seconds and the burn will start.
Er high pressure systemet armeret? Ja, det har ikke det er noget på noget tidspunkt. Mystisk. Skal jeg ind og tjekke? Ja, tak. Check.
Alright, this is flight. We have a small hold. We were not able to pressurize the fuel tank. Just stand by.
Data. Ja. High pressure CSI. Okay, come back. Very clear.
Yeah. Pat, we need you up here.
Pat here, I'm on my way.
We have a little issue about the pressurization because we don't seem to get the pressure on the fuel tank as expected, so it is being investigated manually by the guys at the test stand. We are using helium as a pressure gas, and that we could maybe we could use NO2 or CO2 for the fuel, but as we have to use helium for the LOX tank, as LOX has so low temperature, it will simply freeze all other gases than helium.
This is Pat, I'm in position.
Or hydrogen.
Okay, trying.
Definitely humming activity.
But do you hear the click from the Yaxa?
Try 2 more times, please.
Any reaction?
Not sure we're getting any reaction from the Yaxa, over.
Weird. I'll just try the Yaxa itself on itself.
Please proceed. That one's working.
Okay, then I'll try regular power or pressurization.
Oh, I am sorry. I'm told I was.
We can pressurize, but it's extremely slow, so it won't work correctly.
That's absolutely not correct. That's a power.
Okay, so this is Pat.
I meant N2. That is nitrogen.
Could you try to give it a notch on the oxidizer tank just to make sure if we have different operation, over?
But nitrogen has boiling.
So we want to get fuel up first.
At around minus 200 degrees, so it will shrink when it is blown into the oxygen tank.
Please stand by, we'll just check the lines. Hold.
Okay.
There was a question from the chat. Isn't it difficult or isn't it dangerous for the guys standing inside the test stand right now with all the fuel and locks and the tanks and the pyro installed and so on? But actually no, because we have an issue with the pressurization system right now, which means there are no pressure on the fuel tank and no pressure on the LOX tank, which means they are not dangerous right now. But of course we don't fill the test stand up with a lot of people, but only the necessary personnel.
Flight LOX her.
Go LOX.
Kan vi få en status på, hvad der sker?
Ja, men vi har lidt problemer med at få tryk på fueltanken. Vi får tilsyneladende ikke ventilen fra højtrykstanken, altså magnetventilen, den åbner tilsyneladende ikke korrekt til skift.
Ja, det kan jeg godt se. Det er lidt et problem. Slut herfra.
Flight pad.
Go pad.
Please give it a few attempts more at pressurizing the fuel tank, over.
Okay.
Working, but extremely slowly. It's like the HIDAC is almost closed constantly.
Wait. This is Pat. Try and give it another shot.
Slightly better, but not something we want to run with.
This is Pat. We did another corrective action. Please try again.
Okay. Still quite slow.
This is Pat. Please hold. We're doing maintenance.
Okay. There's about 4 bars on the fuel tank right now.
Noted. Thank you.
There was a question on the chat why we're not using GOX, that is gaseous oxygen, to pressurize the LOX tank. Well, if you've seen the launch of Nexo 1 rocket this last summer, you will see the result of pressurization with GOX, because that was actually what happened. The rocket won't fly very long. We stopped at 1500 meters and went straight down in free fall to the Baltic Ocean. Actually, we will try, after this burn has been commenced, we will try to show you a video from the launch of the Nexo 1 rocket at the Baltic Sea this last summer, where you can see a teaser, a very short but intense description of what happened when we were out there on the sea and launched the rocket. It's very interesting to see.
data pad.
Yeah.
One pulse on the fuel high deck, please.
Okay.
One more, please.
That made a difference.
All right, don't touch anything else, please.
I won't.
Well, we're not sure exactly what they did up at the test stand, but they were kind of working on it for a bit, and then suddenly it worked. So
I think the problem is fixed. Please try and resume pressurization. The test stand is cleared and evacuated.
All right, we'll pressurize fuel tank. This is much better. Now we're at 17 bars.
okay,
All right, this is
now it
fine.
works
We
again.
will commence. The fuel tank is pressurized. All right, we'll pressurize the LOX tank. We are at full pressure. We will commence 30-second countdown in 3, 2, 1, go.
30 seconds to burn, and yes, we're using helium as
25.
pressurization gas.
20 seconds. 15. 10. 9. 8. 7. 6. 5. 4. 3. 2. 1. Ignition.
That was a good and nice burn again, and you saw the purging at the end with a big blast of fire. That's actually just a tiny amount of fuel that is blasted out of the system to be sure that there's nothing that can burn when we come back.
Pressureless, you may approach.
And pressure has been taken away, and the test stand is cleared for approach, first by the pad leader, and then when he say it's okay, everybody can come to the test stand and look at it and kiss the motor or whatever.
Okay, the test stand is safe and a photo can approach.
And remember, this is only photo who can approach. Flight foto her. Go photo. Vi er færdige. Alright, thanks. Then the test stand is open.
Well, it seems we are kind of preparing for the next, the fourth burn. It will be very beautiful because it's getting dark in Denmark. The time is 5:15 in the afternoon, and it's almost dark outside. But in the meantime, while they are preparing and looking into some interesting stuff we can follow, we will present you with our interesting teaser video from our last launch of an actual rocket, the Nexø 1 rocket, the first one we have launched in 3 years. It is the most technically advanced rocket we have ever built. It was a test, and during the flight, that's no secret, during that flight we had a problem because pressurized the LOX tank. We didn't get enough pressure on it, and you will see that when it slowly climbs majestic to the sky and turn around and dive to the Baltic Sea with 530 kilometers per hour. That is a teaser we will show you in a few seconds.
Kan folk komme ind og kigge, hvis de har lyst?
Hvis booster er okay med det.
Saturday, the 23rd of July, we launched the Nexø 1 rocket from the Baltic Sea. It was a beautiful day, excellent weather conditions. Enjoy the pictures and the videos here.
Yeah, we're right in the middle of the LOX loading process, and that little hissing sound you can hear behind us, that's the liquid oxygen already in the tank boiling off slowly through the vent valve.
Power plug is inserted. Nexø 1 power is internal, over.
Order sequence start.
T-minus 10 seconds. T-minus 5 seconds. Ignition.
We are losing power. This is Fido here. I have no altitude on the rocket.
Kommer ned, ja, vi kommer ind til os. Der er ingen go. Der er intet.
We have a rocket in free fall. The parachute is going on. And we have splashdown. Blå rib, ser du det?
Yep. Der kom den op igen. Vi rykker.
Den koger.
Low rate, we have a substantial log spoil off. As it is, we have a diver in the water who's securing the vehicle. Den skærmer også. Ja. Den er tung. Godt job. Jeg har det. Bare lad gå. Pis. Det er slet ikke godt, at starte. Vi har kejlen! Vi har kejlen! Vi har den!
In a couple of weeks, we will have an in-depth video covering the entire Nexus 1 launch campaign. It will present some of the data that we downlinked from the rocket. You can look forward to it.
Is that cold outside? Regeneration? I think it's about 35 degrees Celsius. You guys don't even regen wants to cool it here. That's great. So you feel you could put your music down? Yeah, you can do stuff. Yeah. I wouldn't dare. Lun? Ja. Man skal lige passe på solen. But not on the same layer. Those are all the yeah, I saw that. That's very cool. I can work my hands. Yeah.
Well, that was the teaser you saw there. And I can see up at the test stand they are still padding the rocket engine because we are preparing actually for test number 4, and right now they are analyzing any outer signs in the engine. Has it taken any damages or what? But in the meantime, while we are waiting, we will show you a burn of the until now longest burn from the BPM5 engine. It was during the summer. It was a 35 seconds burn, and it should come up here in a few seconds.
On October 10th, we put our BPM5 engine through its longest burn to date. Over 35 seconds, it provided more than 180,000 Newton seconds, running at a steady thrust, slightly above 5 kilonewton.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition.
Hvad brænder vi ud? Lock switch?
Nå, det var da mindre end 40 sekunder, var det ikke?
Jo, lidt mindre.
That was lock switch.
Den er blæst ud. Jeg tager tryk.
Ja. Så bliver det jo tør for fuel, eller hvad?
Ja.
Så bliver det jo også næsten tør for trykgas. Han flyver bare tilbage.
Experimental. Ja. Det kan virkelig Nå, gå back into the software side. Because I have done some
Jamen, det kommer ud sammen med det bliver blandet sammen med
very passionate about
Altså ude på.
I hate vi ser det der.
Nå, jeg har hørt det for at køle tanken ned, så er det bliver til luft.
Nå, okay.
Og så det der bliver ud ved siden af containeren, så ryger ud igen derfra. Så det står hele tiden og damper ind, og det bliver varmt. Der er ikke noget til at køle andet end bare isolering på.
Så vi kører den varmere end de der
at the beginning when sort of not
vi skal prøve at se på et tidspunkt, hvor langt vi kan der viser vel lidt mere marked i det der bil.
Det bliver ved med at blive tryk op, hvis man lukker tanken.
Basically, if I change something,
Det der sker en forandring.
Det er rigtigt, at de her 25% de er der kun for at holde
Vi lukker tanken før vi flyver, og så sætter tanken på. Så vi har tanken åben der tiden, indtil vi begynder at tælle ned. Lige før vi tæller ned, så sætter vi tryk på tanken, slukker dem og sætter tryk på.
It's not my calling or my pain.
Fordi den der, det er så den, vi skal flyve på, så den skal ikke, det er den tilfælde, vi ser på. Den genkendelse, vi har så den oprindelige frontnet, den kan vi godt være lidt under. Den er også udsat for hårdere og forsøg på at slå det. Ja, jeg er lidt inde på blogget her, at vi kører de her eksperimenter, der skal gøres. Dem kører vi tidligere. Så hvis der er tid til senere på, det vil sige, det er, så vil ikke sådan et eksperiment.
Occasionally someone has to make a
Det er jo virkelig ikke hensynsmæssigt. Det er virkelig hensynsmæssigt. Det speaker er det er klart, hvis man er fuldstændig klar, at man kan godt bygge på den, men det er ikke vigtigt for den. Vi er egentlig ved at samle data og øve os til det. Men det er vigtigt, at vi ved, at vi har det her vegne.
Yeah, now I have like a stand up that you can electronically see.
Den er baseret på en eller anden fra 50'erne. General Director, MDT, det er en styremotor.
Ja, velkommen.
Det er nogle store motorteknik for os, der ikke kan bevæge. Ja, sådan nogle små
Wilson, Jakobskift.
Kom, Jakob.
Wilson, er du travlt optaget dernede i øjeblikket, eller når du tilbage til den næste i løbet af en 20 minutter skift?
Jeg er bare lige nødt til noget. Jeg er tilbage om 5 minutter.
Mange tak, mod til slut.
de nemmere mådes op. Ja. Det er der en del raketter, der har haft succes med. Og det er, ja, det er sådan en, vi har kigget meget ind til. Ja. Men når I så bygger Beta, hvad er det så? Har I så nogle andre, I baserer det på, eller? Det er for tidligt at sige. Det kunne være, hvis man får foreningen, kunne det være beslæget. Ja, ja. Quick sat på. Ja. Ja. Men altså det vi laver lige nu, jo der er den der begyndelse på sommer, men det handler meget om at få der første stræb i sommer. Alle systemer på. Alt det der skal sidde og skabe, og ikke lage motorer og for det til at finde. Ja. Det er en af de små raketter, jeg ser på. Ja, det viser, det kan egentlig bare sætte direkte ind i store.
There's a question on the chat if we would like to bring up the fuel to 100% to get a better cooling, but actually the thermal capacity of ethanol is only half of that of water, so we wouldn't get better cooling. Actually, we would be we would get a lot worse cooling. So that's one of the reasons we have water in the fuel. The other reason is that it brings down the combustion temperature. But of course, if we could use 100% ethanol, then we would have a lot more power on the rocket engine, and the ESP would be much better. But we can see that they're preparing for the fourth burn in the night time of here in Copenhagen. Might be quite beautiful out there, but in the meantime we will show you a very short video referring to the earlier mentioned launch of Nexo 1 from Bornholm, because during the flight we received a lot of telemetry from the onboard computer, and these data was collected and made into a simulation of the flight. And this simulation is actually very good, demonstrating a free fall of a rocket. So we will try to show you this animation made a few weeks after the launch, and it's rather impressive, I will tell you.
T-minus 10 seconds. T-minus 5 seconds. Ignition. We are losing power.
Den kommer ned nu. Jeg kan se. Den kommer ned.
This is Fido here. I have no altitude on the rocket.
Kommer herned, ikke?
Kommer ned, ja, vi kommer ind til os.
Der er ingen go.
Der er intet.
We have a rocket in free fall. The parachute is very down. And we have splashdown. Ser du det?
Rather impressive, isn't it? That was the video from the data we collected from the rocket. The actual data collected during this flight, if we hadn't received it through radio, we would have to find them on the bottom of the Baltic Sea, because the avionics section was ripped off the rocket during the impact, and it ended down on 70 to 50 meters of water. So we will probably never find that again.
Det er meget, er det ikke support som radio, altså vedligeholdelse af råstokker og husninger og huslerne er jo meget. Ikke om inden, det kan nok. Det er jo det, altså der er ikke nogen andre, der vil flytte noget på den måde. Der er 3 kilometer til højde. Det er jo huslerne rigtig dyrt. Og jo, vi får mange penge på billige, som det egentlig får mange penge på.
Well, as you see, the test stand right now, there's still people around the test stand because there's no danger out there right now. And you can see that the test stand number sign has already been changed to number 4 because we're preparing for the fourth burn. In the meantime, we will show you a short video of Flight Director Thomas Petersen telling about the roles of a flight director.
Go flight.
My name is Thomas, and on the next mission I'll be working as the flight director. And so flight director is a name, fancy name that we adopted after NASA. No reason to stand back from NASA. So essentially my responsibility will be to make sure that the mission runs according to a predefined checklist. So we have in advance we've made a complete checklist from essentially from the night before the launch. It starts with the final checkout of the Nexø rocket and of all the subcomponents and all the subsystems that are required to launch it. There's a lot of radio communications, there's a lot of electronics, and computers that have to talk together in a big grand network to facilitate the launch. And so, as the flight director, it's my responsibility to oversee that everything happens according to schedule. And on the day of the launch, I will be on board Vostok, our mission control ship. And from there I will sort of lead the program for the day. And so in the morning we'll sail out. Sputnik will sail out first, Vostok will follow. And once we're at the launch position, then I will take charge and I will guide the pad leader on Sputnik. I'll guide him through the necessary preparations to make the rocket ready. And that means a final checkout before launch. Then we'll fuel the rocket, and after fueling it we will load liquid oxygen. Then the whole crew will clear the pad, and once the pad is cleared, then we will do a fast automatic pressurization and launch the rocket. And after that we will recover the rocket once it lands in its parachute. And as the flight director, it's my responsibility to oversee all of it and make sure that it happens according to schedule and that nobody does anything where they can harm themselves. That everything happens according to schedule. And a very important part of the schedule is also to contact the air traffic control in Malmö, because it's so that we're shooting in a naval shooting terrain, and it has been cancelled for ships and also for air traffic. And so to coordinate the closure of air traffic, we have to contact air traffic control in Malmö. We have to contact them in the morning before we sail out. We'll contact them again about 60 or 30 minutes prior to launch, and at that point they will cancel the airspace and close it off for civilian air traffic. And So that is a very important task on our list. So once the rocket has been launched, it will make its way to 8 kilometers of altitude, and then on the way down it will unfold its parachute and land at sea. And we will know where it lands from our FIDO system. That will give us a GPS location, and then I will relay that to our fast-going small boats, and we have 2 or 3 on the day, and they will quickly, within a couple of minutes, make their way to the landing site, and then they will recover the rocket, and also recover the nose cone, which lands in its own parachute. And so it's also part of my responsibility to coordinate this recovery operation between mission control and our small-going fast speedboats.
Ready? As you see, the pyro technician is just installing the pyro in the engine. It's as earlier spoken. It's just a kind of New Year's Eve sparkle generator. It's not anything explosive or anything. It's electrically ignited, and the sparks from this will ignite the fuel and LOX mixture in the pre-stage, during pre-stage, and when we can feel the pressure from the chamber has risen to a certain level, we will automatically ramp up the power and go to what is called the main stage, where we go to 100% thrust or higher. During the first burn we had at least 20% more power from the rocket engine than it is designed for, and during earlier burns we have tested this kind of rocket engine very many times. During a earlier test, we, by an accident, we ramped it up to 9 kilonewton, and that is almost 200% of what the engine is designed for. But it still survived and was able to deliver a lot of other burns later on. So this 5 kilonewton motor is maybe really more rated to 7 to 8 kilonewtons, maybe, if we can cool it steadily.
Flight, Boxer.
Go LOX.
Så er der fyldt HB-gas på.
Tak for det.
It seems they have refilled the HP gas.
Are you still
with the high pressure helium system.
Roger.
Fueling is complete.
Thank you.
We are using a
Pyro. Pyro is installed.
We are using a dynamic pressure regulation system, which means we have a very high pressure helium tank that is changed to maybe 17 to 20 bars at the fuel and LOX end of the system. Because of this DPR system,
You can
we are
turn on your slow speed cameras.
we are able to pressurize the tanks very fast, and
We're at step 39. Can you confirm nitrogen purge line pressure at 10 bar or more? Over.
Confirmed and confirmed.
Roger.
early on we had to pressurize very slowly when we had filled up
Do you
the
have an eye on
tanks.
the test area? Is it safe? Over.
The test area looks very much safe, yes.
Thank you.
And the new system with the
All
DPR
right,
system,
this is
we
flight. We are about to load locks, so all non-essential personnel should leave.
now with this DPR system we are able to instantly
Fly pad.
pressurize.
Go pad. All non-essential personnel out.
All right, booster, are you ready for launch loading?
Booster is ready.
Photo is also ready. Thank you. Locks, are you ready for launch loading?
Ready, yes.
All right, locks vent valve is open. You are go for 55 liters. Over.
55, we're go.
As soon as the fuel and LOX is loaded, we can just pressurize the system with through the DPR system. And the really interesting thing is that with this system we can keep
We are now
the nominal pressure
constant. With a bit of luck, we'll fire in about 10 minutes, and then we will clean up. Over.
So we are ready for, almost ready for the fourth burn of today. Until now we have had 3 long perfect burns, and later on we will collect the data and see what we can learn from it. As you all know, we have had a valve that stuck, and actually we've had 2 different valves that stuck, but with a bit of work, nothing special, it just worked perfectly again afterwards. The view you see now, you can see the test stand inside a container. It's a 20-foot container, standard container. We have cut a lot of holes in it and mounted cameras mostly outside, but also on the container, and that's maybe the reason why they shake so much. The interesting part about this test stand is that we can move it into our workshop, and that we can change the installation and tubing and change tank and re-insulate and so on in the hot or semi-hot environment we have in our workshop. And then when we are ready for test, we drive it around and place it where we have the possibility to make these tests. In this case we have enclosed it inside a container, so if we should experience a spontaneous disassembly, as it is called, or CATO, when the chamber explodes, all the shrapnel from the explosion will be contained inside the container. That is what a container is for. If you like watching these tests and videos and feel the sound and so on, you ought to think that this is actually volunteer that are doing this job. We are a volunteer organization and no one gets paid for doing this. It's only we're doing it in our spare time, and we use a lot of our money on it, but the thing that makes it possible is actually the many small donations we get from all over the world, and if we are to launch more and larger and more advanced rockets in the future and make better and better tests and video streaming, we simply need more money, and we would like any of you who watch this to consider paying a little of money, donate something to us. You can see how to do it on our website, copsup.com, and we would really appreciate any donations, as small as $1 or $10. That would be perfect, but sometimes we get a lot of things, $1,000 and so on. We are really happy about these things, because it is an expensive hobby we have here, and we're trying to share everything we do with the world, with the other enthusiasts. So please consider donate money to us, please. For those who don't know what the whole project is about in Copenhagen Suborbitals, I can tell you the plan is actually to be the first amateurs on this planet to send a human being into space in a suborbital flight, and take this astronaut back in safe and good condition. Whether it'll be a man or a woman, we don't know, but we definitely will never send animals up into space. But our goal is actually to send a human being out into the space that is above the Kármán line at 100 kilometers height, and bring the person safely back again.
Thank you very much. Photo, this is flight. Photo here. Please turn on your high-speed cameras. And Pyro, please stand by for igniter arm. Over.
When you see this fourth of our tremendous burns this day, you might consider that this is actually only a small step on the road to the universe, because this engine is only 5 kilonewton, and for the space flight we are planning for with a human being on board, we need an engine that is 20 times as powerful, 20 times more powerful than this engine. This is gonna be a big engine, and we need money to support this development of this gargantuan motor.
Thank you. Pyro, you may arm the circuit, over. Will do. Flight, Pyro. Go, Pyro. Pyro is armed and VI is clear. Thank you. Alright, this is flight. We are about to pressurize the system.
We're ready to pressurize system. Please note how fast we are actually pressurizing. Earlier it took maybe 1 or 2 minutes
ready for go, no go?
or more.
Crowd Alpha, go, no go. Crowd Alpha, go. Booster, go. Water. Water test, go.
Water fire suppression, go.
Photo. Photo, go. Pyro. Pyro, go. Data, go. Alright, we have a green board. Pressurization is imminent. System is armed, and we will pressurize the fuel tank. Alright, Pat, I'm sorry to trouble you, but we have the same issue with the high deck, so we need to do the same, over.
Pat, understood. Booster, please meet me at the test stand.
Unfortunately, we have a stock valve again.
You may approach the test stand.
So we have a small hold. It's not long, but last time we were just working a little with the valve, and then it worked again. So let's hope it's the same issue again. There's a question concerning what the goal of this test is. But it is testing of the DPR system. Are we able to completely control the pressure and the flow, or the flow through the motor of fuel and LOX in the correct ratio by regulating the pressure in the tanks precisely? Are we able to do that? And if we're able to do that, is there any other issues and so on? We will look at the data later on, but it's very important to have the exact correct ratio of fuel and liquid oxygen when we come to the test flight of Nexø 2 coming summer.
Fuel. We can wrestle it loose.
Okay. It's working now, thank you. Alright, fuel tank is fully pressurized, 16 bar.
flight. This is pad test stand is evacuated.
Thank you. We will pressurize the lock tank.
Now we're pressurizing the LOX tank, and then it gets
Lock tank is pressurized.
dangerous.
We are about
No one
to,
is on the test stand.
countdown. Countdown commencing in 3, 2, 1, go. T-minus 30 seconds.
This is the fourth burn of today's test.
T-minus 20 seconds. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition.
Perfect burn again. Really nice deep sound here where we're sitting, and it seems the engine has survived another of these very long burns. So we're just waiting to depressurize, and when the pack leader has
test stand is pressureless. You may approach.
yeah, booster looks at the test stand and makes sure it's clear for approach.
Okay, test stand is safe and photo can approach.
Alright, this is flight. This more or less concludes the operation for today. It was the last test, and by eyeballing it, it looks like it went perfectly well. And we will now close down and pack everything up.
Mission control to stream. Just a short update on what flight said. It looks like we had 4 more or less nominal burns. We had a little trouble with the valves because we actually have a too fast turnaround time. They do not have time to actually get to a normal temperature, and it is bloody cold in Copenhagen today. But all in all, everything has been working as it was supposed to, and we're ready to crunch some data. But it looks like we have had a successful test with ramping up of the pressure in the engine, ending at around 16 bars. And now we have a lot of data that we have to go home and look at. So thank you very much for joining us today, and hope to see you next time. Mission control out.
Flight photo. Go photo.
This was the last burn of this day's tests. We have had 4 successful burns, and actually only minor issues concerning valves we will have to look into, and we have a tremendous amount of data now we can analyze with pressures and temperatures and flow rates and so on for a lot of ramping up the pressure in different ways. We cannot come into detail with that, but we will surely come up with interesting data on our homepage and so on. And furthermore, we are just packing together, cleaning up, moving the whole thing back to our workshop, and we will close down. We thank you for watching, and you have to remember this is a volunteer organization. We live on donations from people all around the world, so please visit our homepage and see if you can is able to donate something to us. We would be very happy. And furthermore, we will just look forward to show you other tests and launch this summer in our process trying to send a human person into space. So thank you for this time, and see you next time.